Okay, YouTube, in this video we're going to focus on solving polynomial inequalities. In the past we've looked at polynomial equations, that is, these equations such as this one here, f of x, where we've got x squared minus 7x plus 10, this polynomial expression, and what we often do is just set the y value equal to 0 to solve for the x values, or the x-intercepts, or zeros, or whatever you want to call them. But basically in the past we've looked at equations. In this video, focusing on inequalities, what we really mean are saying, can we find all of the x values, go solve all of the x values, for which our y values are either less than 0 or greater than 0. Or we could say for which our y values are less than or equal to 0 or greater than or equal to 0. But basically, we say that a polynomial inequality is any inequality that can put in one of these forms here, where we're really just saying, can you find all of the x values for which our function has positive or negative y values? That's all this is really mentioning here by saying greater than or less than or 0. So when we look at this graph over here, when we consider the graph of f of x equals x squared minus 7x plus 10, this parabola that opens upward here, we can use a graph to easily kind of find the x values that we're looking for. And the reason why is because you can see clearly on this graph, you see this inequality right here. It says this is where our function x squared minus 7x plus 10, or f of x values, has positive y values. And you can see those portions of the graph here in blue. And we can see below the x-axis, this is where we have solutions to this inequality, where we say our y values are actually less than 0. So we say this is really just some expression in y, and what we're really doing is finding the x values for which our function here has positive or negative y values. So what you notice here is that 2 points are listed here. We call these boundary points, or at least that's what they are called in this image. What we're going to do is we're going to give them a different name. We're going to call these critical values. Okay. So when it comes to solving polynomial inequalities, what we're really going to do is this. We're looking for all of the x values for which our function has positive or negative y values, which ones we're concerned with here. And so we could see that for this graph right here, where it has positive y values, we could say it's all of these x values right here. When you plug those into your function, those are going to cause your y values to be positive. Or it might be the case, we're asking the question, where does our function have negative values? We could say it's all of these x values right here in the middle. Those are the ones that cause our y values to be negative. So that's what we're looking for, these x value intervals for which our function is caused to have positive or negative y values. And what I notice is it can only ever change from positive to negative y values, or negative to positive y values, at these points here. And we recognize these as basically being zeros. So what we're going to do is we're going to put a definition of critical values here. But basically, critical values, in a nutshell, critical values, if this will pop up here, are values where our function, critical values, I'll type this in here, x values at which our function can switch from having positive to negative y values, can switch from having positive to negative y values, or function values, we'll put that in parentheses, function values, and does not have, well, we don't have to put that in here, does not have to switch. What I basically want to point out here is this: your function has to switch from being positive to negative or negative to positive at a critical value. And we say these critical values basically happen at the zeros of this function. So because they happen at the zeros of the function, what we're going to do to solve these is we're going to look for these zeros values of x for which our function maybe switches, and then we're going to test to see if they actually switch. So the procedure for solving polynomial inequalities, this is quite long, but what I hope to do is boil it down into a nutshell for us. But basically, the first thing we want to do here is get the right side equal to 0. So the right-hand side equal to 0 is what we want to write here. So right-hand side equaling 0, right there. This must be true before we solve these, but it says solve the equation f of x equals 0. In other words, what we're going to put right here is solve for zeros, or solutions is what we call zeros sometimes. I'll try to squeeze an I in here. Solutions, or we say x-intercepts, basically. Solve for these values here. And so what we're going to do is we're going to locate these boundary points on a number line, and it says thereby dividing the number line into intervals. So remember, we're saying find all the x values for which our y values are positive or negative. So basically these two values right here take the entire x number line, and what they do is they split that x number line up into 3 intervals. One interval from way out here up to there, another interval from here to here, and then a last interval from all the way out to the right to here, basically. So we're going to use those critical values to set up what we call test intervals. So set up test intervals is what we're going to do next. And then basically what we're going to do is we're going to choose an x value, and we're going to call this a test value. It's an x value from each interval. And what we're going to do is we're going to plug that into the initial inequality, and we're going to see if we get a true or false statement. And the reason behind this is basically because, let's say for instance I want to find all of the x values for which my y values are negative. It would be on this interval right here, but I know that my function right here between these two zeros is not going to go from being negative to being positive again, because it would have to cross over a y value of 0 to get to positive again. So if I were to check an x value in here, take that x value and plug it in, and I find out that my function value is indeed negative, then I know it's negative for all of the points between here. And if I plug it in and I find out it's not negative, then I know that for all of the x values on that interval, it's not negative. So basically, what we're going to say here is this: we're going to choose a representative x value and plug it in. So what this says here is if the x value is positive, then f of x greater than 0 for all numbers of x in the interval. And if the f value is negative, then all of our y values are below 0 or negative for all of the x values in that interval. So number 5 here basically says write the solution set, selecting the interval or the multiple intervals that satisfy the given inequality. And so it says only as a note here, this procedure is valid if less than is replaced by less than or equal to, or greater than by greater than or equal to. You do the same thing. So putting all these steps together, I want to show you how quickly we can do this. But looking at this, it says solve and graph the solution set to this. So the first thing we're going to do is this: we're going to get a 0 on the right hand side. So we say x squared minus x. I'm going to bring the 20 back over here, and we say greater than 0. So this is our initial inequality. Now what we're going to do is we're going to solve for the zeros. So what that means is x squared minus x minus 20. We're going to set this equal to 0, and likely, hopefully, fingers crossed, we can factor this. And so this one does factor into x minus 5 and x plus 4. And I notice that, of course, when I set x minus 5 equal to 0, I get a solution value of 5. Or when I set x plus 4 equal to 0, we certainly get a solution value that is negative 4. We could just say that by looking at these because of our factor theorem. But these right here, what we're going to write here is these are my critical values. And actually, I don't have to write this because I left a little thing up here. We say our critical values are at negative 4 and positive 5. So we say, what are our test intervals? Well, what we're going to do down here for the solution graph is we're going to draw the x-axis. And because all we're after are x values, that's the only axis we really need to draw this graph on. So I'm going to go out 1, 2, 3, 4, 5 to the right and 5 to the left here, because it seems that I can fit both of my critical values on here. And what we're going to do is this: we're going to put open dots. Well, actually, let's just do this. Let's label negative 4 here. Negative 4 and positive 5. These are our two critical values. And I'll put little x's here for now instead of dots. These are our critical values. And what I know is it splits our number line up into intervals. So our test intervals would be these. And the interesting thing is it starts way out on the left and goes up to negative 4. But we don't include negative 4 because our function is equal to a y value of 0 right there. We want to find all the y values, in this case, where our function is greater than 0. So we would say here's this interval, and then negative 4 to the next 0 here, which is 5. And then from that 0 here, from 5 out to infinity. So two critical values basically means you're going to have 3 intervals, because you'll always have one more interval than critical value since it's splitting up the number line into these. So I didn't write this on the line, but these are the test intervals. So now what we're going to do is we're going to choose a representative x value from each of these intervals, and we're going to test them. So notes purposes, I would say that these, we're going to refer to these as the test values that we're going to plug into our function. So in terms of what values I would choose here, I would choose these. I would choose one value to the left of this critical value, so negative 5. Here I'm definitely going to choose 0 whenever possible. And then I'm going to say x equals 6 out here. We'll choose these values and plug them in and see if we get a true statement. So we say negative 4 is a test value. We're going to test 0 for sure, and we'll test 6 as well because they lie on these intervals. So plugging back into the initial inequality here, we're going to have to do this 3 times. Oops, I don't mean to write an x here. But basically, let's do this. We're going to plug in here negative 5. And when we plug in a negative 5, what I notice is I get a 25 minus a negative 5, which is plus 5, minus 20 is greater than 0. And so I get 30 minus 20 is greater than 0, or that 10 is greater than 0. And so since this is indeed true, this is a true statement, then this point right here is part of the solution interval. So what we're going to do is we're going to shade all of the points to the left of this point here. And I'll come back to what we put as a boundary quantifier on here. But when we test 0, testing 0 is pretty quickly done here. We say 0 squared minus 0 minus 20 is greater than 0. From this inequality here, we get basically negative 20 is greater than 0. And certainly this is false. And so we wouldn't shade here. And I'll tell you what, when you plug in 6, we can kind of overwrite these 6's here. It's not negative 6, but we'd say we get 36 minus a positive 6 minus 20 is greater than 0. Or in other words, it would imply that we get 30 minus 20 is greater than 0, which is so true. And so we would shade to the right side of this. So the only thing we have left to do is basically at negative 4 and positive 5. You notice that this is just a greater than. And because it's just a greater than, what we're going to do is we're going to put parentheses on this. And we're not going to include those values because if this had said greater than or equal to, we know that our function is equal to a y value of 0 at those points. And so since it's equal to a y value of 0 at those points, plugging them in, we would get 0 is greater than 0, which is not true. So we're not going to include them. And so our solution intervals for this particular function are negative infinity to negative 4. We say in union with 5 to infinity. Cheers.